So what is the problem? So only 4 students are there. Is there any drive is there today? Anyone? Kumar Reddy?
Yes, sir.
Is
We
it?
have pre-placement talks. Action, sir. 9:30 AM.
అర్థం కాలే ఒకసారి చెప్పరా మళ్ళీ
So there is
We
a
have pre-placement talks. Sir.
ప్రీప్లేస్మెంట్ టాక్ ఇస్ దేర్
Yes, sir.
9:30 AM.
ఓకే ఇట్స్ ఆడియో వీడియో రికార్డింగ్ కాబట్టి సో ప్రాబ్లం లేదులే లెట్ దెం టేక్ ఇట్ లేటర్ ఆన్ ఆల్సో సో ఐ విల్ కంటిన్యూ అవర్ క్లాస్ okay let us start and we'll look at what is the lecture number? It is lecture number 7, I think, right? It is lecture number 7 from unit number 2. So let us discuss about determination of pull-up to pull-down ratio. Pull-up to pull-down ratio of an nMOS inverter. nMOS inverter driven by another nMOS inverter. nMOS inverter. So sometimes this is very important to understand that somehow we have designed an inverter, right? Somehow we have designed an inverter, right? Okay. So if you want to actually use this inverter in a circuit, then we should know what is the capability of this particular device. That means whether it is is it able to transfer whatever the input signal to the output side comfortably or not. Okay. Especially in case of when it is connected to another load or maybe another circuit. Okay, so that means whenever is so students, is there any background noise is there coming from my side? Can you please check?
No,
Did you
no, no.
no okay, fine. So this device is should be able to drive the particular load, for example load or maybe another circuit. Okay, so if this inverter is wants to drive the another inverter, wants to drive another load, something like this. Just a second, is your EMS is calling. Okay. Now the question is that how much load that I should apply to this inverter so that whatever the input is there, that will go to the output side comfortably. Okay. So this is actually the practical scenario that normally existed in a circuits. That means whatever the circuit we designed, the circuit, I suppose here the circuit is only one transistor, one NOT gate only we have considered. But whatever the circuit that it is, that should drive the load. And what is the maximum load that we have to apply? Sorry, what is the minimum load that we have to apply for that one? Okay, so therefore we have to maintain that. Of course, not a minimum load is what is the maximum load that we can apply for that one. So that's also we can see. So how much load that I should apply so that the signal transformation is proper, or I can say that the good transformation can be possible, right? So in this case, we considered the load is actually another inverter, right? The thing is that we have considered a node, and we are applying another load is actually another inverter is. Okay, so therefore this is the scenario we have considered. This is the scenario considered. Right. So as I mentioned that this inverter is an nMOS inverter. This inverter is actually an nMOS inverter. Okay. So nMOS inverter is if you consider that nMOS inverter means only depletion load pull up only we are considering, not resistive load, because resistive load has got some problems. So that's the reason why we are considering only for the nMOS inverter. Okay. That means so we have a load, we have a depletion mode transistor, something like this. As everybody knows that, and this must drive another inverter having the same type. Okay, so this is what actually my output V out. This is my VIN. So I am connecting the output of this one to this one. Okay, it is VDD. Now the question is that what is the size of this device? What is the size of this device? That's what we have to keep in our mind. How much load that I should apply for an inverter so that the signal transportation is proper. Clear? Now, how do we do this one? So in the worst case condition, both the transistor must be on. Okay. So therefore, suppose one transistor is on, one another transistor is off, means so in that condition we don't have any good accuracy in it. Okay, therefore what we have to do is that when both the transistors are on, then only we are considering the conditions, right? Now, so for the sake of understanding, I'm going to write here is VIN1. Okay, so this is called Vout1. Here the input is called VN2. This is called Vout2. Okay. So the first inverter input is VN1. The second output, the first inverter output is Vout1. Second inverter input is VN2. The second inverter output is Vout2. Okay. So as we know that Vout is equal to Vout1 is equal to VIN2. Agreed? Because of the connection, something like this. This is the voltage at which both the transistors on. When both the transistors of this device on, for example, N11, N2. This is called N3, N4. If N1 and N4 should be on, what is the condition? And absolutely it should be on, both the transistors must be on. This is observed that whatever the input voltage that we apply, okay, for example, this is called VANV, inversion voltage. For example, VN1 is equal to VN2 is equal to VN some voltage. That voltage is equal to VDD divided by 2. That means the maximum voltage divided by 2 will make sure that both the transistors of N3 and N4 are on. Agreed? That's what we have seen the VA characteristics. We have seen the VA characteristics, something like this. So not VA characteristics, the voltage transfer characteristics we have seen like this. So exactly 0, and for example, it's VDD maximum voltage. Exactly at VDD divided by 2, we are make sure that both the transistors are on. That means both the transistors are on means, as we know that both the N1, N3 and N4 are in saturation. That's what we studied about in the previous class. Okay, if you recall that voltage transfer characteristics, voltage transfer characteristics of nMOS inverter, this is what we observe. At the middle point of the maximum voltage, both the transistors are on, and we say that both the transistors in saturation. So this is the point where it is possible to find out the size of the N3 and size of the N4. Agreed? Okay, so now let us consider now. So under this condition, what condition? Under this VAN is equal to VDD divided by 2. Under this condition, both the transistors when VANV is equal to VDD divided by 2, both the transistors becomes on. Both the transistors becomes on, the two in saturation. The two in saturation. Clear? Okay, so if N1 and N2, what is the both the transistors in the sense I can write it as N3 and N4. Please remember that. N3 and N4, both are in saturation. So what is the saturation current equation for N3? What is the saturation current equation for N4? N3 is a depletion, N4 is enhancement. What is the saturation current equation of N3? For example, ID, I'll take this diagram, and here I'll write copy, and I want to paste it here. See here. So here is a ground, this VDD, and this is called VAN2. Okay, this is VAN2. Fine. So this current, whatever the current we are talking about here is IDSD, for example, depletion mode current. What is the current here? We can call it as IDS enhancement, right? So therefore, since both are in on, this is a series connection from VDD to ground, right? Therefore, VSD is equal to IDSD is equal to IDSE, right? Both currents are equal. So what is the current equation for this? The current equation for IDSE is equal to beta by 2. I think better to write in this way. Okay, no, don't want it. K into W by L into VGS minus of VTD, depletion mode transistor threshold voltage, whole square by 2 is equal to, okay, right, this is equal to, what is the equation here now? K into W by L divided by 2 into, I think it'll write in half and less than better. Half, that is also half, I'll write it here. Yes, and half VGS minus of VTN enhance VT and VTH whole square. Right, so this is what we normally look at this. Okay, so now here we have to do something. Okay, just to we could say that these half and will get cancelled, K and will get cancelled. Okay, now we want to find out the WBL ratio of, for example, this is the depletion mode type of transistor related. This is a enhancement type mode transistor related. Okay, or for simplicity, I'm writing in this way. For simplicity, I'm writing this. This is a pull up, right? Pull up. This is a pull down, right? Pull up ratio and pull down ratio. Generally, W by L ratio is called aspect ratio. Aspect ratio. Normally, this is how we will call it as. But the inverse of this L by W, we will call it as the W by L ratio. We will treat it as a Z. It's not impedance. It is the size of the device. Generally, this is what the terminology we use for this one. Okay. Therefore, ZPU stands for the L by W ratio. L by W ratio for the pull-up network. Okay, that is called L by W of pull-up. Okay, next, ZPD stands for length to width ratio of pull it down. Right. Now, according to this one, we will modify our circuit. Okay. Now, let us do this one. So W by L ratio can be called as, this is called as 1 by ZPU. Are you agreed? So what is the here W by L ratio? The pull-up is nothing but, it is nothing but W by L, but we want to L by W. Therefore 1 by ZPU we can write it in this way. Fine. Now what is the VGS of the depletion type mode transistor? VGS is nothing but VGS. So what is the VGS here now? The depletion mode transistor VGS is equal to gate and the source are at the same potential. That means that is 0. That is 0 minus of threshold voltage of a depletion type mode transistor whole square, which is equal to, what about this one? W by L, 1 by ZPD, pull down transistors, transistor L by W ratio is multiplied with, what is the VGS of this transistor? So VGS is nothing but it is available from gate to source, right? So gate is at VAN2. What is the VAN2? So VAN2 is actually is equal to VAN1. VAN1 is equal to VDD by 2 again. Okay. So can we write like this? It is nothing but VDD divided by 2. That is what VGS minus of, that's what I'm talking about here. Next, VTH whole square. Is it clear to all of you? Yeah. Now, I will write it here in this way. I want to find out ZPU divided by ZPD value is equal to n. So for that one, what I have to do is that, so I have to turn this one this side. Okay. Minus of VTD whole square divided by VDD divided by 2 minus of VTH whole square is equal to ZPU divided by ZPD. So everything is known values only. Since we know that, it's very important, we know that VTD is actually a minus 0.6 times of VDD. This is the typical values. Since we know that typical values. Okay, now VTH is nothing but 0.2 times of VDD. Generally 0.2 times of VDD it will be for nMOS transistor. Okay, so how do we write like this now? So therefore, if we substitute this one in the equation number 1, so minus 0.6 times of VDD whole square divided by, so VDD divided by 2 minus of 0.2 times of VDD. What is the value that we'll have? This is called ZPU divided by ZPD. Okay, what is the value now? This is 0.6 times of This is what is the value? 0.36 times of VDD square. What is the value now? 0.5. This is 0.5 times of VDD, right? 0.5, 0.3. What is the value that we have written? What is the value? Can anybody guess what is the value of this one? Anyone from the class? Please try to tell me what is the value that I'll get. What is the ratio? I'll get it here. Chapala. I think this is 0.3. 0.5 minus 0.2. 0.3 times of VDD. 0.3 times VDD whole square. So, what is the value? Simple mathematics second. 0.36 divided by 0.90. Antela?
0.09, sir.
0.09. Into
Yes, sir.
VDD will get cancelled. So what is the value of this one? ZPU divided by ZPD. So this value becomes 4 divided by 1. You simply write in the ratio. Okay, ZPU divided by ZPD. So what it says that here is that ZPU value is equal to 4 times of ZPD. Agreed? That's what it says that. Okay, that means that, for example, these are the two things that we remember. One thing is that we have to maintain the pull-up to pull-down ratio is 4:1. What does it mean? If we consider pull-down network is 1 unit, pull-up network must be 4 times we have to consider. What does it mean? So, since we are talking about the worst case condition, because both the transistors are at maximum, it's operating, maximum operation is available at the saturation region only. So in that sense, I have to consider in this way here, we'll write here. Here, what we can consider that if you say that, okay, all these are not required. Okay. So if you consider its ratio, its size is 1 unit, its size should be 4 units. Okay, length to width ratio. What is the length to width ratio here? If the bottom transistor is 1 unit, if you consider, upper transistor should be 4 units. Then only whatever the signal that is coming from input side, VIN1 to VOUT2 comfortably. Otherwise, it's not possible. Okay, that means we have to sacrifice something, right? So this is called determination of pull-up to pull-down ratios of the size ratios of the nMOS transistor driven by another nMOS transistor. Therefore, what we have to keep in our mind that whenever we want to drive to another inverter, so this inverter size should be 4:1 that we have to maintain. Clear? So then only the signal transportation is possible very comfortably from the input side to the output side. I hope you understand this concept. Okay, so this is a small topic related to the pull-up to pull-down ratio of an inverter, that to an nMOS inverter. Any doubt, please let me know. I will explain that concept. Hello, Arupa. So any doubts, please let me know. Is it clear to all of your concept? Is very simple. No need to buy heart, no need to do anything. Just only understand the concept.
సార్ ఫస్ట్ ఇన్వర్టర్ కి ఈ రేషియో మెయింటైన్ చేయాల్సిన అవసరం లేదు సార్.
అంటే ద ఫస్ట్ రేషియో అనడానికి అవసరం లేదు. వెన్ ద ట్రాన్సిస్టర్ అనేది డ్రైవ్ చేయాలి అని అంటే యాక్చువల్గా ఇట్ ఈస్ బెటర్ టు మెయింటైన్ దట్ వన్. ఓకే, వెన్ ఎవర్ వీఆర్ కన్సిడరింగ్ ద nMOS ఇన్వర్టర్ ఇస్ డ్రివెన్ బై ఒక్కొక్క nMOS ఇన్వర్టర్ తీసుకోవాలని అంటే జస్ట్ వీ హ్యావ్ టు మెయింటైన్ దట్ వన్ ఆల్సో. ఓకే, యా, ద ఫస్ట్ వన్ ఇస్ ఆల్సో విల్ టేక్ దట్ 4:1 రేషియో. ఓకే, అంటే ఏదైనా ఒక ఇన్వర్టర్, ఇఫ్ యూ కన్సిడర్ ఎనీ ఇన్వర్టర్, but the two nMOS inverter having the pull-up network is depletion, pull-down network is enhancement అన్నప్పుడు compulsory we have to take 4:1 ratio. Yes, we have to take 4:1 ratio for the first one also. So అంటే ఎంతమంది మెయింటైన్ చేయాలి అనే చేయడం కోసం this is the experiment that we have done. So this is the setup that we have done. Okay.
Yes sir.
In fact, if you want to do it for any circuit, not only inverter, if it is an AND gate, if it is an OR gate, or if it is an adder, something also we can do it, but it's very complicated nature. But this is the procedure how we have to calculate in order to drive to another device. Okay, that particular driving device, the size we need to calculate from this setup only. ఇలాంటి సెటప్ తోనే మనం చేయగలం, డెరైవ్ చేయగలం. దట్ మీన్స్ అదే ఇన్వర్టర్ని, సో ఏదో ఒక ఇన్వర్టర్, ఐ హ్యావ్ డిజైన్ సమ్ ఇన్వర్టర్ హియర్. సో దీని యొక్క క్యాపబిలిటీ నేను ఐడెంటిఫై చేయాలంటే ఏం చేస్తా అంటే ఐ హ్యావ్ టు టేక్ అనదర్ సిమిలర్ ఇన్వర్టర్ హియర్. ఓకే, సో దెన్ ఫైండింగ్ దిస్ వన్ ఇస్ అప్లికబుల్ టు దిస్ వన్ ఆల్సో. దట్స్ వాట్ ద థింగ్. Okay, now shall we move on to another approach, another method? Okay, so far we have seen an inverter. One in the different type of inverters that we have seen. One inverter is resistive pull-up. The second one is depletion pull-up, because the depletion pull-up is better compared to the resistive pull-up. But the depletion mode type of transistor also consumes a lot of power. Actually, it consumes a lot of power. Okay, therefore, what is the problem? But we cannot use this depletion mode type of transistor if the power requirement is very stringent. That means the power consumption is less devices. This device is also not applicable. Why? Because there the two reasons are there. Since depletion mode type of transistor, if you are using, it is always on. Why? Because the channel is already present, which means that it is as soon as the power supply is given to the device transistor, automatically on. So therefore, we have to deplete the charge, deplete the channel, so that we can utilize. That means opposite inversion of that particular enhancement mode. Okay, so therefore we have to there is a problem with the depletion type mode transistor. Another problem is that the short circuit power consumption is high. What do you mean by a short circuit power consumption? So let us look at here. So short circuit power consumption. So whatever we have designed here, let us talk about short circuit. Short circuit power consumption. So whenever there is a path is existed from pull up to pull down ratio directly from VDD to ground, from VDD to ground. So therefore this is called the short circuit path is existed. Because of this one, there is a short circuit current. Short circuit current. This lead to short circuit power consumption. Okay, so that means whenever we are realizing a circuit, it should not allow direct path from the VDD to ground by switching on all the transistors. So let us explain this one with this diagram. For example, we have seen a depletion type mode transistor, an enhancement mode type of transistor, right? So when VAN is equal to 1, for example, logic 1, what could be the Vout value? Everybody knows that. We're expecting that 0, but we don't get 0 value. Some non-zero value will be there. Okay, approximately 0 we can consider. Under the situation, what is the state of this transistor? This is on. Okay, this is also on. When both the transistors are on, the current of depletion type and enhancement type both are available. That means that there is a short circuit is existed from VDD to ground, right? Agreed? So therefore, this will lead to some power consumption. Okay, so this power consumption should not be there in our circuitry. So how do we solve this problem? We will see later on. For the time being, this is a problem. So apart from the depletion, since the depletion mode type of transistor is always on, okay, so there is a power consumption is available. To avoid that problem, we are going to use another circuitry, and that is also having the same problem, but we will look at that one later on. Okay, now we are going to look at enhancement mode pull up of an nMOS inverter. So what we are going to do is that, so I don't want to use the depletion type mode transistor. I want to use enhancement mode nMOS transistor. What is the problem? We can do it also. Let us look at here in this way. Enhancement means we take, this is how we can do it. It is connected to VDD. This is connected to, so this must be always on. So if you want to say that this is always on, okay, what I have to do is that we have to be, since it is a load and this must be always on, for that reason I have to connect this one to VDD. I want to make this is on VDD. So later the people will realize that why can't we use, why we are using the enhancement mode. So depletion mode type of transistor we have seen, whatever the unit, how many units, if you take X here, or if you take some, so P here, okay, so 4 times of this one we have to consider. As we know, the size we have to consider 4 times. That means the size of the depletion type mode transistor in an IC also will increases, right? So that must be avoided. So in order to do this one, so pull-up network ratio will be equal to the pull-down network ratio if you are using the enhancement type mode transistor. It is not necessary to use 4 times of the bottom transistor. Here N1 N2 N2 need not be a 4 times. Okay, that's the reason why I have, since the area concentration, okay, so area consideration and power consideration. So these are the 2 problems can be solved by the enhancement mode type of transistor. Okay, but short circuit problem is already existed, but somehow if you remove some particular portion of the power, then it will be advantageous. So in that sense, we have come with this particular circuitry. So here also the operation is the same. What is the operation that we can see here? The operation is when Vn is equal to 0, everybody knows that. What is happening here? What is the condition of N1? N1 is equal to, okay, N1 is equal to N1, N2 both are on, yes. Okay. What is the value that will have it? Sorry, I'm sorry, extremely sorry. Here the N1 is on, sorry, off, but N2 is on, right? N2 already VDD on the kada. Okay. So therefore, what is the current flowing through this IN1? IN1 current flowing here is 0, which makes IN2 also. Therefore, what we can observe that. So V out is equal to, what is the value? V out is equal to, ఈ వాల్యూ అవుతుంది షార్ట్ సర్క్యూట్ కదా, ఇక్కడ ఏమవుతుంది మనకి the current flowing, better we can write it in this way. So in the sense that since IN2 is equal to 0, which leads to the voltage drop between drain to source is equal to 0 for the second inverter and a pull-up inverter. Okay, what it leads to that? That means that the drain potential of the second inverter, second MOS transistor, and source potential at the second transistor must be equal. But here you can observe that. See carefully here. For example, if this is the VDD, I could write it in this way. For example, here we are connecting VDD. Here is actually VDD is available. How much value that we observe? That's the question. That's what the scenario is observed here. So one point is at the drain is at VDD, source is at V out, and this is called VDD. Okay. So what is the maximum value that we observe here? Is it directly VDD is observed here or other than VDD? In order to check that one, it is very important to know that just a second. Okay. So therefore, whether this VDD is going to this side or not, we need to check. But as we know that it's very important to understand from the perspective of past transistors. When it is an nMOS transistor, the source must be at a low potential and drain must be at high potential. That's what we observe. So we treat this so we treat this as the gate. This is the drain, so that we consider. But it's generally what we are at. The source is at less than that of the potential. So source be at less than that of the drain potential, as we know that. So that means that VD should be less than VS. Sorry, I'm sorry, not like this. VD should be greater than VS. That's what the simple fundamental. Okay, then what is the voltage that we have to apply? What is the maximum voltage that we have to apply? For example, if the drain potential is observed at this point, suppose if it is transfer transfer. Then what is the condition of this transistor then? As everybody knows that if the transistor is set to be on, okay, VGS value should be greater than threshold voltage of a transistor. But if VDD is transferred to the source side, something like this, what is the value that we observe? VG minus of VS that I want to calculate. VG is nothing but VDD. VS is also VDD. Okay. Threshold voltage is actually 0.4, non-zero. Okay. Normally the 0.4. Okay. What is the condition here now? It will be 0. The difference is 0.4. The comparison what should be there? Less than. If VGS is less than VTH, does this transistor is on? No. Transistor becomes off. So what does it mean then? So whatever the potential that we're applying at this point, it cannot reach us to this side. VDD cannot. So that means that whenever we have a source is at VDD, sorry, gate is at VDD, one side is VDD, other side should not, we cannot get VDD. We cannot get VDD. So what is the maximum value that we'll get it here? So what is the condition that both the transistor becomes on? As we know that VGS is greater than threshold voltage. Okay. So what is the VG here now? The gate voltage, the source voltage greater than VTH. Therefore, the source value I want to find out. What is the maximum source voltage? Therefore, VC I can come in here and minus VTH you can get it here greater than VS, right? That means VS value is less than VC minus of VTH. Agreed? Until whatever the source voltage that we are observing at this node, this should be less one threshold voltage less compared to the gate voltage. Okay, so then we can make sure that the transistor is on. That means what is the according to this condition, according to this situation, that means if this is at VDD, this is at ground VDD. So therefore gate potential is required. That means what is the VS value here? VS value is less than what is the value that we'll get? VZ is nothing but VDD minus of VTH. Okay, that means that you are expecting that whenever we have a the enhancement mode type of transistor, something like this VDD and this is the VDD, what is the value that we'll have here? What is the value we'll have here? It's VDD minus of VTH is observed. And a less than VDD minus of VTH we can observe. Not more than that one. Right? So therefore, we can make sure that this much value that we can have. For example, if you, so this condition, whether this condition is making this transistors on or not, we can check again. Okay. Therefore, VC, we know that VC is greater than VTH, should be there. And what is the value of this one, VC? VDD minus of VTH, right? So this is what we can say, and VTH. So these two will get cancelled. Minus threshold voltage. VTH is equal to VTH. That means the left hand side is equal to right hand side. It is greater than or equal also. Okay. In that case, both the transistors. That means so left hand side and right hand side both are equal. Therefore, what we can say that the transistor is always on. Okay. That means this voltage will make sure that the transistor becomes on. So that's the reason why for nMOS transistor, if one terminal is at VDD and another terminal, the gate is at VDD, other terminal is VDD, then the maximum voltage that we observed at the other terminal should be VDD minus of VTH. This is called threshold loss problem. Threshold loss problem. Okay, one threshold value less out now. Therefore, what we observe now here, what is scenario? If this condition, if you consider this is the situation for P, and if you paste it here, what is the value that we observed? What is the value that we observed? V out is nothing but VS2. VS2 that we observe here is that VDD minus of VTH. VDD minus of VTH. So therefore, what we observe that V equal to 0 or loss is 0 if you apply, Vout is equal to VDD minus of VTH, right? So this is what we observe. So anyway, but another one is when Vn is equal to 1, both the transistors are on. If both the transistors are on, it is obvious to understand that Vout is not equal to is approximately equal to 0, not equal, not actually, it's not exactly equal to 0, approximately equal to 0. That means that if you are using the enhancement pull-up, if you are using enhancement pull-up, both, please remember that both the logic values are degraded. Okay, logic high ki logic low value ki రెండిటికి ప్రాబ్లం అవుతుంది. ఇందా రెసిస్టర్ లో అన్నప్పుడు అట్లీస్ట్ లాజిక్ 1 అండ్ లాజిక్ హై వాల్యూ అనేది బాగా వచ్చింది. లాజిక్ హై వాల్యూ అంటే VDD వచ్చాయి. బట్ ఇక్కడికి వచ్చేసరికి ఏమవుతుంది, లాజిక్ లో వాల్యూ యాజ్ వెల్ యాజ్ లాజిక్ హై వాల్యూ బోత్ విల్ హ్యావింగ్ సమ్ ప్రాబ్లం. సో we never use the enhancement pull-up network in your inverters. Clear? So therefore, because of both the things are not at all acceptable, so I don't want to go for more detail about it. Just we have to consider that Vn and versus of Vout. Okay. So actually, this is what VDD, for example. But what we are expecting that VDD minus of VTH, it will start. VDD minus of VTH, it will start. But inverter characteristics remains same. Okay. Something like this. Okay. This is what we observe. VOL, this is called VOH. So VOL is also approximately equal to 0, not equal to 0 exactly, approximately equal to 0. That means non-zero. I can write it as VOL is not equal to 0. That's what we observe. So we are expecting that. So this is what we expect. This is what we normally expect. But it's not like that. So there is a problem here. There is a problem here as well. So with this, we come to the end of the today's session. We will discuss the remaining things in the next class. If you have any doubts, please send me the question form. Yeah. Tell me.
So actually today we have an Accenture replacement talk, sir.
Yeah.
So most of the students have attended that.